So as Leonard said, my name's Zach, and I wanted to tell you about some work that we've been doing over at UW for a couple of years on trying to verify distributed systems. But first I want to start off by mentioning that I played a relatively minor role in the work. There's a bunch of people involved. All the credit really goes to the students who are absolutely incredible. Been a ton of great people working on it. Okay, so what are distributed systems? I feel like I hear, I actually just finished undergraduate admissions committee work yesterday. And we saw these first-year freshmen who said they wanted to study distributed systems. I'm not sure if they, actually know what those are yet, but it's a hot buzzword. So what's going on? I think a lot of times in the common conception, a distributed system is this thing that runs in the cloud at some data center that's powered by a river or, hydroelectric dam or something. But actually, most uses of a modern computer are, made possible by distributed systems. So basically, every app that you use every day, your traffic is going through a distributed system. Now, this is mostly done to support scaling, but we don't just use distributed systems in order to support, billions of users or whatever. We also use them when we really need to tolerate failure. So whenever we need replication, in order to ensure that we'll continue to maintain service, even when things go wrong, we use distributed systems. So this seems great, but it turns out that distributed systems are really hard. So on one day in the summer of 2015, the New York Stock Exchange crashed. Now, you couldn't read about it because the Wall Street Journal website also went down. And if you were worried and trying to escape, you couldn't get off the ground because United was forced to ground all flights. This is in one day, and all of these systems failed due to bugs in their replication in the distributed systems. So what's going on? We have these really important platforms that a lot of people depend on. There's huge amounts of engineering effort invested in them. Why can't we get it right? Well, it turns out that distributed systems are just sort of fundamentally difficult. So you're running multiple processes on different nodes. So you already have the challenges of message passing concurrency. And there's some good techniques for that. But on top of that, you also have all kinds of failures that you don't really have in other domains of programming. So for example, messages can be dropped, they can be duplicated or reordered. Machines might crash, they might crash and then come back. They might crash and come back with stale state, they might crash and come back with new state. And the total set of possible behaviors is just sort of too big to effectively test. So word of mouth is that folks at Google spend something on the order of $1 billion a year testing just a couple of their most important distributed systems. And they still sometimes have bugs that show up in production. And so everybody kind of ends up pulling out their hair. Now, that's not going to work for me because I don't have a lot of hair left. So my students took pity on me and said, we got to figure out a better way to go about this. And of course, we're at Deep Spec, so you guys know the punchline, right? What we need to do is figure out how we can prove these things. If testing isn't going to work, and it's a really important system, there's really only one game in town, which is formal verification. So how are we going to do that? And that's really what we want to sort of start talking about today. So mainly what we're going to focus on is how we formalize distributed systems. And what I want to try to convince you of this morning is that it's really actually not that hard. The techniques you guys have already been learning this week are totally up to the task of building a nice model where you can actually prove things about a couple of simple systems. And then later in the week, the sort of take-home point that I want to convey is that there's actually this nice form of modularity. I think this is what Adam has called vertical composition. So what we can do is we can sort of hide details of failures. We can separate the concerns of doing application-level programming from fault tolerance in a really nice way and get proofs that compose pretty nicely. So the idea here is that you'll be able to develop your system. The developer will sit down and write their code imagining they're in this world where faults don't happen. And then we're going to be able to transform that system automatically to get another version of the system that does tolerate faults, right? So we're going to be able to eliminate that assumption about no faults. So just to try to give some visual intuition before we get going in the Coq code, I wanted to show a brief animation of a distributed system running. So this is an instance of the Raft protocol. And you can see a bunch of things going on here. So we've got 5 nodes. And there are these timeouts that asynchronously cause things to happen. The nodes exchange messages. And we also have state, which is constantly changing. And it's not forced to be consistent by the network, at least, in any way across the nodes. On top of that, nodes can fail, right? So this is a pretty simple system, right? It's just 5 nodes, and it's trying to do some kind of consensus. But you can imagine that things get pretty nasty when you start to scale up. And there are examples. So the traditional response to this has been model checking. And that's where a lot of great work in TLA and by Leslie Lamport and others has been applied. But there have been, even fairly recently, people have found counterexamples that require something like 40 steps to get to with, sort of the standard model checking techniques. So we want to do better than that. We want to avoid the kinds of failures that bring down stock exchanges and websites and airlines. And so what we're going to do today is kind of build up a simple model of Verity. And then we'll talk more about Verity proper later in the week. And I think next time we'll talk about how to do these transformations. One thing that I do want to do, I think, pretty early is mention a unfortunate name collision. So in Verity, there's also this thing called a VST. And this is very bad, right? So Andrew had precedence. He had it first. And the last time my hands were on the paper, it was VDST, for Verified Distributed System Transformer. So I might slip up and say VST. And we should imagine that the scope we're currently in causes that notation to resolve to Verity's Verified System Transformers. OK. So here we go. So to get started, what we're going to do is figure out what the heck a distributed system looks like. So what is a distributed system? When I go to sit down and write one, how am I going to model that? How am I going to build implementations of distributed systems in Coq? And one thing we're going to do, maybe a little bit differently than what some of you might be familiar with, is we're actually going to do this in terms of modules and functors rather than the type classes that I think you've seen people talking about so far. And that's going to mean we have a couple of little weird things. So one thing is that we're going to define packet way up front here. That is the wrong way. And so a packet is, this is a very coarse-grained approximation of the thing you put on the network, right? So it has a destination, and it has some kind of payload, and that's it. Now what we're going to do is define the types of things that go on a distributed system. So like in any sort of system you care about, you want to think about what's externally visible, right? What are the things that the system does that you're going to write specs about? And so for that, we're going to have a couple of types here for input and output. We have some set of nodes in the system. Every node is going to have a local state. And nodes can internally exchange messages. So notice right away that we've already made some choices here. In particular, messages are not going to be things that come from clients. So we have a separate type for interaction with clients. And input and output are also separate types. And we'll see at the end of the week how maybe this wasn't such a good idea. But for now, we're going to be able to get away with it. Here's one trick that I think is worth mentioning. Maybe folks already know this. So right now, we're defining a module type. But I'd like to have a definition based on the parameters that are in the module. And I don't know if folks have played much, but you can't do that in Coq. So instead, what you can do is you can define notations in the module type that are going to let you kind of get away with the same thing. OK, and so that's it, really, for the core of a system in terms of the main types, right? So we have some input and output type. We have some type of nodes. We have states. We have messages, packets, and handlers. So the other thing a system's going to need to do, this is just decidable equality for a couple of things the semantics are going to want, is define the handlers. So the first kind of really simple handler is just the init state. And what this is going to do is it's going to tell us when the system starts up, what's the state look like? What's the state of every node? How do things get going? And then we're going to have two different kinds of handlers. So we're going to have one handler that takes something from a client and gives us back a handler, and another thing that takes something from another node, takes a message, and it's to give us a handler. Now, if you look here, see if I can get them both on screen. Do these types suggest something to anybody? Yeah, exactly. So I heard some people asking questions about monads. I'm not entirely sure what the background is for everyone in the room, but that's exactly right. We're going to define a monad, and I thought we might step through it a little bit gently in case people hadn't seen it before. And this is a nice example of using modules. So what we've done above is we've defined the types of two modules, base system params and system params. And you see where we split it. We did that for a reason, right? So the things in base system params are just type definitions. They're pretty straightforward and easy to write down. On the other hand, for handlers, we want to write code. And it has to have this certain structure. And you're going to end up having very deeply indented code if you don't put it in a monad. Yeah?
Should I think of handle input as handling input to a node or handling input from a node?
So you should think of input as every node has a local channel to the outside world. And when it gets an input, it comes in on that channel.
So it's input to a node.
Input to a node. Yeah, exactly. Input to a node from the external world. So it only interacts with other systems by messages being exchanged. Okay, so now what we're going to do is we're actually going to define a monad, so it's going to be a lot easier to write these handlers. Oh, and that reminds me, please do ask questions as we go. The exercises for this are pretty open-ended, so I really want to make sure folks understand the model that we're building. Otherwise, it might be a little bit tricky to do some of the extensions that are in there. Okay, so one of the things you got to be careful with modules is to make sure that you you almost need to keep things kind of linear, right? So you want to make sure you include everything, and if somebody else is going to build upon it, you're going to need to export it, which is what we do here, right? So now we're defining a functor. We're going to take those base system params, right? Remember, those were the basic types. What's input, what's output, what's a message, what's a node. And we're going to export all of those, right? So when somebody's defining their system using this monad, they'll just instantiate the functor, and they'll be good to go. And we'll see an example of that in just a second. Okay, so a monad, for folks who don't know, is actually pretty simple. We're not going to do a full monad tutorial. But basically, you can think about it as stuff wrapped with other stuff, okay? So in this case, what are we doing? Well, when we write a handler, what it's going to do is that node is going to get its current state, and it's going to produce a new state as well as messages to send to other nodes in the system, so packets, and outputs to send to its external client at that node. And so what we're going to do in the monads, we want to be able to break up writing those handlers into smaller, simpler pieces. And as we do that, each of those small, simple pieces, we want to collect what it does, right? So that's what the monad is going to do for us. And we can already see a really simple example of it. Like here, we have ret, which actually doesn't do anything, right? It just puts a value into the monad so that code in the monad can get access to it. So ret is going to be, for some type, which is implicit, is going to take that value, it's going to put it in the monad, and it's not going to change the state, right? So we're going to wrap up the exact same state. We don't send any messages, and we don't send any outputs. Yeah. Okay, so as an exercise, can anybody help me write bind? Now, from the type, we should sort of be able to figure out what it does. Right? Bind has a couple of type parameters. It takes something that's in an A handler monad, and it takes a function from A's to B handler monads, and it produces a B handler monad. Yeah?
Yeah, we'll need a function which takes state first.
Does everybody understand why this is?
Intranet, basically. Returning a monad.
Who said intros? Yeah, so I mean, in some sense, it's, you know, whenever, let's go back over this type, right? We're going to end up with a handler, which is going to be from state to this sort of result type. And here in the monad, we always, you know, we're going to have to start with a state and get that result type, right? So this is sort of introing. We're getting the context that node was in when it started. Okay, I have the function. What's next?
Now when you're going to apply MA to S.
Right. So what's that going to give us?
It will give us like a quadruple.
This is going to be A. This is going to be what? Packets and outputs? Okay.
To apply F on
Okay.
That we need to take the packets from that and probably and same with the other. And return the most recent.
Okay.
Actually, we need to apply not. I mean, we need to now I think update. I guess like a state because I think currently it doesn't say. No.
What do you want to do?
I mean, I want to put like S after.
Here?
Yeah, like this.
Okay.
It's Kamma is missing.
Sorry?
Kamma is missing after the DS. Right.
Oh, thank you. Okay.
Yeah, now it's quadruple. So B, then S prime. And something.
Yeah, so, okay, so if you did not, okay, if you completely understood why we're stuck here and what happened to get up to this point, please raise your hand. Okay, if you don't have your hand raised, actually, let's everybody raise their hand. That's pretty good. If you don't have your hand raised, look at the people around you who do have their hand raised and make sure that you grab them during lunch. Okay, so what we have to do now, right? So remember, we're going to use this for defining our handlers. So when we sit down to write the code, it's going to be kind of in this DSL. So we need to make sure that we capture sort of what's going on. And the intuition, right, is that when I run something in the monad, I'm going to produce sort of these outputs, right? I'm going to produce a new state, some packets to send, and some outputs to send. So if I've done A followed by B, what's the total set of packets that I need to actually send? Is it just these, the final set that I ended up with? Is it? Ah, there you go. That's right. Let's see, I think that's probably correct. It looks about the same, right? Wow, that's a big space. How long do I have to hold this down for? Nice, you guys are good. Okay, excellent. So for people,
There's one difference is in one hand we have A from S and the other we have F from A from S.
I guess that, you know, one of those are going to be shadowed, right? But you're right. Maybe we should make it super clear, just so that we don't accidentally apply it to the wrong state. But this brings up a good point. Suppose that we did apply it to the wrong state, right? Suppose that when I was defining bind, when I'm defining this DSL that I'm going to use to write the handlers for events in my distributed system, suppose I made a mistake in the bind. Am I totally hosed?
Because the one mistake can be fixed everywhere by just making the one definition.
So that's a good point, right? Defining libraries like this, these monad libraries, is nice because you can sort of improve one thing and it's a rising tide that lifts all boats. But really what I'm trying to decide is, suppose that we had gotten this wrong. Suppose that instead of applying to S prime, I accidentally applied it to S, right? And then I went off and I told people, you know, hey, I verified this thing in my framework. You should use it.
That'll be bad.
Would it?
Some proof wouldn't work.
There you go, right? So this is something I want to emphasize as we go through this code, right? It's important when you're programming, especially in Coq, especially if you're thinking about critical, you know, any kind of critical system, including distributed systems, pay attention to where things are delicate. right? Kafka is this amazing mechanism